Recall how we first defined the area under the curve when we dealt with calculus of one variable. The area under the curve is approximated by the area inside these rectangles, but it's not such a great approximation. As we use thinner and more rectangles, we can get a better approximation of the area under the curve. However, what if we want to approximate a graph of a function in 3 dimensions? What kind of rectangle could we use to approximate the volume under the surface? Here is a typical 3D rectangle. It seems to approximate pretty well the volume under the surface and in the region of the base of the rectangular box. Notice that its height is determined by the value of the function at a point in the base of the box. The height is then f of x sub k comma y sub k. We could put a whole bunch of 3D rectangular boxes together, the height of each box dictated by a point on the surface. This is an approximation of the volume, but it's not a really good one. As we choose more and more rectangular boxes that have smaller and smaller bases, we get a better approximation of the volume. And even better, in the limit, this is the volume under the surface given by f of x comma y in the area partitioned by the bases of the boxes.
We were talking about these multivariable functions that were these rate functions that were like a rate of change per 2 quantities. So I just kind of made this up. So like this surface here, you could think of this as maybe rate of change of mass of mold in grams per degrees Fahrenheit per day. Okay, and so then our independent variables are temperature degrees Fahrenheit on the x-axis, time in days on the y-axis, and then the z values of this surface are like they're like rates of change of mold mass per both independent variables. Okay, so that surface kind of looks like this. Just so you see, that's like an angled plane like that. Okay, so we were saying we were calculating like little changes in the dependent variable. In this case would be m, mass of the mold. Okay, so how would we do that? We did that by taking, say, changing these up into changes in temperature and changes in days. Okay, and so then like that. And so I'm breaking this, it's like made a partition of this region. Say we're interested in, temperature changing from, maybe this is say 40 to 52 degrees Fahrenheit, and then over the time frame from 7 to 11 days or something like that. Okay, and so then we're interested in like how much total mold mass would we accumulate in that case. And so what was that? So that's basically going to be a change in temperature, or so the rate of change of mold mass times a change in temperature and times a change in time in days. And that's going to give us what? A little bit of change of mold mass for that, corresponding to that change in time and that change in temperature, where the rate is the height. And so then at the end of class we were saying, okay, suppose I wanted to use lower left corners to estimate. I'm going to use lower left corners to estimate the rate of change. So for this first one here, where's the lower left? Where's the lower left? Is it exhibit A, B, C, or D? D, that's the lower left. Okay, so we come up here like this, and that would be the height of this thing the whole way. Okay, so would that be an underestimate or an overestimate of the actual mold mass for those changes in time and temperature? Under, because it's falling underneath. And then same, if I stay with lower left, then this one here would be, this corner would determine the height, so it'd be right there, say. And I'd have 4 of those, right? And so then at the end of class, we were talking about, all right, let's kind of make a transition to kind of more a geometry application here. Geometrically, what is this? This is like the z coordinate, right? And what is this d little t? Looks like dy, right? And then the d capital T? dx. And then, so in geometry, what is that? So what is dy dx? Area of the base, right, of this thing. And the z is height. So when we calculate these little amounts of accumulation using this multivariable rate function, the analogy in R3 is height times area of the base, which is a volume of a rectangular prism. Right? So it's like a tall, like rectangular tower. Okay, so when I add up these 4 amounts of mass accumulation, I'm gonna have 4 of them. There's 2 I didn't draw. You said it's gonna be underestimate or overestimate? All 4 of them are not. All those rates are lower than what we can see is kind of the rate over that element, right? That little area element. So how do we make a better estimate? Use a smaller dx and a smaller dy, and then add up more narrower columns, right? More narrower columns will do a better job calculating this mold mass, right? In this case, mold mass. But then the geometric situation, these volumes of these rectangular columns getting skinnier and skinnier for smaller and smaller dx and dy. What do those kind of do a better job of estimating? What is it that we're doing a better job estimating when we make a finer partition of these things and imagine more and more skinnier, taller rectangles that we're adding up the volumes of? What's that? Yeah, it's going to be a better and better estimate of the volume of the whole, right? So the finer we partition up that blue region, each time taking skinnier, smaller dx and smaller dy, skinnier rectangular columns, the tops of those columns are doing a better and better job of reproducing the actual surface. And so then the sum total of those volumes is doing a better and better job estimating the red. Red here. Is the red showing up good? And one more right there. So that as we take us more and more of these, we approximate or get closer and closer to the volume of that red solid. The volume of that red solid, which will be like the real mold mass over that time. If you're going back to the rate of change and accumulation example, the volume of that red solid will be, the value of that will be the same as the mold mass accumulated between 40 and 52 degrees Fahrenheit over those 4 days. Okay, so I want you to find that actual volume just by geometry. Because I gave you a nice plane, we can do this without calculus. So the function is x plus 1. So the function is x plus 1, and the region is 0 to 4, 1 to 3. And I want you to find the exact volume of the resulting So I'll do this in red. So find volume if the function is x plus 1. And I think I said that x is from 0 to 4. Was it 1 to 3? Thank you. So there's the red. You're focusing on the red. That's your task. Find the volume of the red solid if that function is x plus 1. And x is going from 0 to 4, and y is going from 1 to 3. Everyone's working on this?
Imagine, see the right side.
All right, let's see. Austin, did you guys get it? Tell me what your approach was. Okay, good.
So I found the area of one trapezoid,
Okay,
which I got 1/2 times 4.
like this side right here.
Yeah.
So like this closest side on the right. Okay, so you said 1/2.
So 1/2 the height, which should be 4, I think. And then,
The height this way. Okay, good.
and some of the bases, which should be 1 and 5.
1 and 5.
So 6.
Okay.
And then times the width, which should be 3 minus 1, so 2.
That's a valid way to do it. So they started with the area of this side and then just took that times 2. And that gives?
24.
There are other ways to do it. You can split it up into a box and then a triangular region at the top and add them together. But in the end, no matter how you slice it, you should get 24. Did you guys get 24? Different? So there's like geometry of large figures, right? So trapezoidal prism, you could do a triangular prism plus a square prism, but you should all get 24. Are we good? Okay, so now I want to think about this in terms of, so that's geometry. Now I want to think about another geometric approach is adding up a zillion little rectangular prisms, right? So partitioning this thing up into a zillion little squares and adding together the volumes of all those like sticks sticking up. And what would that be a matter of? Yeah, so there'd be like we talked about last time, like a double sum of each of these individual volumes, right? And so that would be what? The rate. So height times width times length. And we could start, say, by going along this way. Say if y going from 1 to 3. So fixing x, and going from y going from 1 to 3. And that would be summing up, right? Summing up. Oh, but I wrote dx dy. So I need to do this the other way. If I'm going to do y first, I need to write dy dx. So I'm basically going to take these and I'm going to sum from 1 to 3 in terms of y, right? So this is for any typical x, right? So I'm going to pick a typical x and sum up those from 1 to 3. Again, summing up a bunch of sticks. And then once I do that, then I'm going to then I'll have a whole row of sticks, right? I'm going to add a whole row. I'm going to take a whole row of sticks. I'm going to add up to all those rows of sticks as x goes from what? 0 to 4. So this is the calculus way of doing it. You're imagining we're summing up really super skinny, tons and tons of really super skinny rectangular prisms to sum up to be the whole trapezoidal prism. Okay, so what does that look like? So that looks like doing two integrals in succession. The first, so you work from inside out. So we're going to do the integral from 1 to 3 of x plus 1 with respect to y first. And so what is the antiderivative of x plus 1 with respect to y? So it'd be with respect to y, antiderivative is xy plus y. So this is like partial antiderivative, right? So x is considered to be a constant. We're doing the antiderivative with respect to y. And then we're going to evaluate that from 1 to 3. And this is still, so this is still this kind of this inside integral with respect to y. And so then I get integral from 0 to 4. We're holding on to that for now. So we're going to plug what? 3 in for y. So we get 3x plus 3 minus plugging 1 in for y, which is x plus 1. And that all dx now. And so I think you get 2x plus 2. Is that right? Is this all 2x plus 2? Yeah. Antiderivative, x squared plus 2x from 0 to 4, 16 plus 8. Lo and behold, what do we get? 24. Okay. So when you do these double integrals, or we're summing up all these a zillion rectangular columns, you work from the inside out. So you set up your integral, and you're going to integrate with respect to your inner variable first. Treat this as a single variable holding this variable constant. So it's like partial antiderivative. And then you do once you've got that expression, then you do the outside integral. Yes, please.
Does the order of the integrals matter?
All right, so so let's talk about that. So can we do dx dy here? So could we do dx first? If we did dx first, that means for a typical y, I was answering your question. No. So if we did dx first, it's like we hold y constant, and now we're going to march across and add up a row of sticks for a constant y. Okay? And that's x plus 1 and that's from what? 0 to 4. And then once I get that, then I'm going to add up a bunch of rows of sticks, starting at y equals 1 and ending at 3. So can work out that. And what should we get when you work that out? You should get 24. Let's do it fast. Here we go. So 1 to 3. X squared plus x. And that from 0 to 4.
It should be x squared.
Thank you. And then plug in 4, we get 16 over 2 is it 8 plus 4? Is that right? So I think we get 12. Is that right? 24. Okay, so that was the long answer. Does the order matter? Well, so because we have constant limits of integration, we have a rectangular region like this, you can just change the order. You can choose x or y first, and there's really no difference in how you set that up, right? So you can just you can choose x first or y first, but that kind of ease of changing back and forth is only possible when you have a rectangular region like that. And we're going to do non-rectangular regions next. Yeah, if it's a rectangular region, you can just swap your order. Swap from dx to dy, swap your limits, and it'll work out. Okay, so what do double integrals find then in a geometric sense? So they find accumulation. If you're talking about rate of change and accumulation, they'll find the accumulation of the quantity. But what do they find in terms of geometry in R3? Volume. Do they find volume? Is that right? Yeah, kinda. No, that's actually the right answer. Yeah, kinda. Why? Is it not volume? Right, Richard. So let's take a look at this. Another example. Are we good on this example? So we showed that geometrically, just a geometric of large solids, and then calculus, 2 ways with calculus, you get the same result, the area of that red thing. So let's look at this example. So this is the function 0.5 cosine x sine y plus 2, and over this trapezoidal region. Okay? So if I do the double integral of f, and say I'm going to do dy dx over the trapezoidal region, capital T, will that give volume? Will that give a volume? Won't we be adding up a bunch of columns sticking up here into the surface, or lining up to the top of the surface, and it'll give us the volume of all that, right? Okay, what if I do this function without the plus 2? What's going to happen now? Am I going to get volume if I do that double integral? Do you see what's happening there? Do you see where that surface, where the purple is a little darker there? That's where the surface is going underneath the xy plane. So what's going to happen for those xy ordered pairs in terms of accumulation, or in terms of, quote, volume? Subtract the positive, it'll subtract the volume. Subtract the volume underneath. Okay? Volume is always a positive quantity. When you do this double sum or this double integral, those function values will be negative, and you'll get a negative contribution to the total, right? You'll get a negative contribution to the total. So how can we qualify this thing as we're saying double integrals give not quite volume, but what? Double integrals calculate. Okay, that's one way to say it. Double integrals calculate, we could call it signed volume. And what does that mean, signed volume? So this is geometry now. We're not talking about it. Yeah, Sam?
It's basically, I don't know how to say it, but it's like not absolute value.
Right. So another way would be like net volume. But what are both those things? What is signed volume or net volume? No. So we're in the geometry realm here. We're not in the accumulation rate of change realm. So yeah, we could talk about all this about accumulation rate of change. But we're in the geometry realm, and we're sticking in the geometry realm. What does signed volume and net volume mean? How would you get that value? You would take what? All the volume above and do what? Subtract all the volume below the xy plane that's carved out. So we could say that subtraction is a difference of volumes.